Yeah, you can continue, Kirti.
Yes, ma'am. I hope the screen is visible.
Yes.
Yeah.
Yeah, so
Maximize the screen. Is there maximize option? Presentation option.
no, this is not in presentation, ma'am. It's in PDF. Maybe I can zoom a little.
Okay, that's fine.
Okay.
Yeah, can continue.
Yeah, okay. So I'm going to discuss about the router today based on its functionality. See, today we will discuss about the functionality of router, what are the inputs present and what are the outputs that is provided, the packet format, and where it finds its place in the TCP model, and how the data are transmitted through the router, and how the input signals look like, and how the outputs from the router looks like. All these we are going to see, and along with that we are going to cover the important blocks that are part of the architecture. Okay, so let me start first. So router is basically used as a communication tool. So between multiple networks, in order to transfer data, we are using router, right? So router will be transmitting data in the form of packets only. Okay, so what it will do, it will get the data from the source, it will check for the address of the destination, and it will route accordingly. It is just redirecting the data based on the destination address, okay, between the networks. So these are the basic input and output signals for the router.
Tell slowly explain briefly, okay?
Yeah, okay, yes, ma'am. So here we have input signals. The input is given in a parallel way only. This means the inputs are handled as bytes. We are sending 8-bit data parallelly here. Okay, so it is the basic data input which is shared. And packet valid means if the data is available, then packet valid will be high. So it will just denote, yes, the data is available and it is ready for share. Okay, suspend data denotes that means if the router is busy with the previous signals and it is not completed the previous transfer, then it will suspend the next occurring data. So if it raises the suspend data, it means it is busy. Or else the data which is transmitted is lost midway. We have some mechanism to check for errors, right? Like we have parity as a common mechanism to check if the data transmitted is reaching the destination or it is lost in the midway. So in such cases, error will be raised. So we can get the error signal.
Could you please tell me why we use suspend data?
Yeah, suspend data. Suspend data means the router is busy with its previous data. It has not completed the previous transmission. Okay, so it is not able to take the next transition, next request, it is not, next data, it is not able to transmit. Since it is already busy with the previous transmit. Maybe the FIFO is full, means I'll discuss about that in detail later. So if it is not able to process the incoming data further, then it will raise the suspend data signal. You got it?
Yeah.
Okay. You understood error signal, right? So if the data packet is lost, if there is some parity mismatch, then error signal will be reached. And clock and reset are global signals, as we know. And we have outputs here, same way. We will deal with the bytes only. So if this is 1x3 router, right? So it will take input from one channel and it is redirecting it to 3 different channels. So we have 3 different ports here. Data out 0 denotes the first channel. This is second, third. So data out is the actual data in which was shared here. Valid out means it is similar to packet valid. Packet valid is only for the single data. Here single data is transferred. Here at output we have 3 different data. So if there is data available in the router for further transfer to the destination, then it will show valid out. Yes, the router has some valid data which is to be read. So if the valid out is high, then the destination will ask for reading it. So read enable also will become high. So read enable is the input and valid out is output. So first valid out will be sent. After that only read will be enabled. Okay, because if there is no valid data in router, then there is no purpose of reading the data, right? So these are the three basic signals in the output. Okay, so I hope you know about the OSI model and TCP IP model, right? I just give a small brief on all these layers. So the original model which was designed was the OSI, and TCP is developed from this OSI model only. So application layer will be the topmost layer where user interaction takes place. Then the presentation layer, it will encrypt the data and it will compress the data accordingly. And session layer is the layer from which the actual communication will begin, right? So during a particular phase of communication, the session will be active. And if there is a gap, small gap, so it means the session is over. So this enables the
Could
communication.
you please brief it slowly?
You want
You're too
much?
fast.
Okay, I'm sorry. Yeah, so I'll start from the beginning. So application layer is the layer where the user is interacting with the device. Like, for example, we are giving some inputs to the inputs in the computer, right? For example, I'm writing a mail and sending the mail to someone. So that user interactive layer is the application layer. Okay, that is the topmost layer. The next layer is the presentation layer. So what will happen there is it will encrypt the data, because user language is different and the computer language it will be different, right? So it will encrypt in a way that it would be received by the destination. Means these 7 layers will be present in both source and destination device. Okay, so in which format the data is encrypted in presentation layer of the source, in the same way only, in the same encryption model only, it will decrypt in the destination. Okay, there are various encryption methods. So the same methods will be used for decryption in the destination device. Then the session layer, the communication will start. So first input the user gives, it is one communication. So the session layer will open, which means that communication is enabled. Okay, means the communication is established between the two devices. So from the session layer, you can go to transport layer. The transport layer, what it will do is, it will get the information from the session layer and it will convert it into segments. Okay, it will break down the data. It will break down the data into different segments. So it forms the end-to-end connection between the two devices. Okay, you have one computer A and computer B, right? So it will form the end-to-end connection between. So it will have data in the form of segments. And here we have network layer. So network layer is the actual layer in which we are going to incorporate the application of router. Okay, what the network layer will do is it will get the data from the transport layer. We have data in the format of segments, right, in transport layer. Network will convert those segments into packets. Okay, so a network will use these packets for communication, and so it will establish connection between both the networks in which the end devices are present. And next we have data link layer. So it is it will check for the speed control, the flow, and errors. If there are any other errors, it will check, and it will give the data to physical layer. Actually, data link also, what it will do, it will break down those packets. Packets will be a little big, right? So it will break down those packets into frames. And then the last layer is the physical layer, where the data from the frames are shared. In the physical, we have cables, like physical cables. So in that, it will be shared as bit streams in zeros and ones. In same way, in the destination device, this happens in the source. In destination device, the zeros and ones data will be taken by the physical layer. Then it will be aggregated into frames in the data link layer. Then those will be collected as packets, then to segments in the transport layer. And after it reaches the session layer, it means one session has completed means one set of data transfer has completed. So presentation layer, now it will decrypt the data to convert the all the data in the user understandable language. So that it will share that information with the application layer, and we will get to know, okay, the response, we have received the response which we waited for which we gave the input. Okay, so these are the 7 layers in OSI model. So TCP/IP is an evolved model from OSI model only. Here we are just using 4 layers. What they have done is they have combined these 3 sessions, application, presentation, and session layers together as a single application layer. Okay, the transport layer is same. The internet layer is nothing but the same network layer in OSI model. And these two are combined together to form the network layer. So widely, I think TCP/IP model is only used. The main application with TCP/IP model is that there is a 3-way handshaking mechanism, which is not available in OSI. It means there is an acknowledgement for every data transfer. So if there is a loss of data also in the network layer, we can find it. It will either generate error or it upholds the reliability of the data transfer.
Could you please tell me the application? I didn't hear.
Sorry? Hello?
Could you please tell me the application of the TCP/IP model? Hello.
Yeah. I think most of the routers use means in most of the communications TCP/IP model only is used. I'm not sure of where OSI is used. I don't have much in-depth knowledge on these network models and all. I just know how these layers are available. If you are specifically asking any doubts, maybe I can get back to you after understanding that.
No, just tell me the application of the TCP/IP. You just said no.
Okay, the advantage you're asking, the 3-way mechanism you're asking. Okay, so 3-way mechanism means like the network layer will be transferring the packets, right? The data is received in the network layer, right? Means the internet layer of TCP/IP. So it will give an acknowledgement that I have received the data. Or if it has not received the data, it will generate an error. No, I have not received the data. It should have means you know, right? Acknowledgement and negative acknowledgement. So if it gives a positive acknowledgement, it means yes, it has received the desired data. So that is an advantage in TCP/IP. Okay, in OSI model, that acknowledgement does not happen.
Okay.
It will just go in one direction only. Okay, it won't check if the data is received there. It won't wait for any acknowledgement from the destination. Whereas it will happen in the TCP/IP. Okay. Okay. So next is the packet. Okay, so we already know that the data is transferred as packets. Let's just see what information is present over there. A packet is actually divided into 3 segments. Okay, so first one will be the header segment, this one. Next will be the payload segment, the data, and the parity segment. The first header segment will hold the address of the destination. So the last 2 bits over here, right, bit 0 and 1, it will denote which destination it has to go to, and the first 6 bits will denote the length of the payload. So see, if there are 6 bits at maximum 2 power 6, we can only have 64 data, means 64 payloads, right? So from 0 to 63, it will vary. It can reach till 63 for maximum, or it can be less than that as well. So how much data is transferred here, that number will be given as length in the first 6 bits. So this forms the header byte. Then comes the payload byte. So see, all the segments are in bytes only. Header is 1 byte, and each data payload is 1 byte, and also the parity bit is 1 byte. So the actual data is transferred here as bytes, and parity is also a byte. Actually, here we have 2 parities. Okay, one is internal parity and another one is this parity. This parity, how it is calculated is, you have 8-bit header data, you have 8-bit data. When, for example, say the length of the payload is 3. Okay, so you have data of 0, data of 1, data of 2, and then you will have the parity byte. So this parity, how it will calculate is, it will do an XOR of this header byte, the first data byte, second data byte, third data byte in a bitwise manner. And it will calculate the parity. Finally, it will load the parity in the payload. Parallelly, whenever the payload is fed into this packet, there will be an internal parity being calculated. How that will happen is, you will have a parity register, okay, internal parity register. First, it will do an XOR between this address byte and the first data byte. That value will be stored in that internal register. When the second data byte is added, that stored value is again XORed. Okay, bitwise XOR is performed with the second data, and it will be again stored in that register. And it will check with the third, it will do an XOR of that stored value with the third data, and it will generate another parity. Okay, this parity generation will occur parallelly, and this parity generation will occur at the end of this packet. So it will check for both the values. If both the internal parity and this parity byte are equal, then there is no error and the packets are received properly. Means the data is received properly. Or else it will generate an error. There is a parity mismatch. So I think you understood the packet, right? The packet structure.
Yeah.
Okay.
Mm.
So this is the actual architecture. Okay. So we have 4 different blocks. Means there are totally 6 blocks. We have a finite state machine, a synchronizer, a register, and 3 FIFOs. Okay, so 3 FIFOs means 3 different channels as output. Okay, so these from this, the destination devices will be getting its appropriate data. So before I discuss in depth about these blocks, I'll just discuss about these input and output signals. Okay, so here we have the clock signal. This is an active low reset. So once the reset goes high, the data transfer is happening. Here you can see this is the data, right? First we have the header byte, then the payload and parity. And whenever the header is started, means whenever the packet is seen, the packet valid goes high, which denote that the data is available for transfer. Okay, and here you can note that the packet valid goes low after the last payload. It doesn't remain high for the parity. Okay, this is very important. Means the packet valid will be checking the packets only for the header and payload. And when the packet valid transitions from 1 to 0, it denotes that the data transfer is done. Now the parity check has to happen. Okay, and this is busy signal. So if the router is busy, that is, if it cannot process these data, it will show busy signal. That's why you can see that header data is being extended beyond this. You can see the payload data are small, but header data is extended since you have a busy line. Okay. So once the busy goes low, the packet is accepted. And here you have an error signal. PM means it denotes parity mismatch. So if this parity is not going to match with the internal parity generated, then it will give you an error. So this is the output. So again, reset low, the same packet valid and data. And these 3 are the output signals. Okay, these are all the input signals and these are the output signals. You have valid out X, read enable X, and data out X denotes the identification of the FIFO. Means you have 3 FIFOs as you already saw in the block diagram. So if valid out is 0, then it says the valid data is available in FIFO 0. Valid out 1 means valid data is available in FIFO 1. In same way for read enable and data out as well. Okay, so once read enable is high, means if the data is being read from this channel, then the data out will send the data, the header, the payload, and the parity. Okay, here you can see all the signals are sampled at the falling edge. The reason they have did this with the falling edge is because of the timing constraints, I think. In order to have the stable data stable, see the router will be means it is sensitive to the rising edge of the clock only. But by the time it reaches the rising edge, the data has to be available. So the stable data has to be available. Means I think you would have known about the setup time and hold time, right? Are you aware of that?
Yeah.
Yeah. So for that purpose, they have chosen the falling edge. But you can also use the rising edge in case you are using some synchronization mechanisms. Like in system Verilog and UVM, we have clocking blocks to provide synchronization. So in that case, the data will be stable even if you try for rising edge. So anything, it is as per your wish. You can choose the rising edge or falling edge. Okay. So now let's go into the blocks. Okay. You have four different blocks. One is FIFO, then synchronizer, register, and the finite state machine. So this is the FIFO. You have three FIFOs here. You get the data in. This could be the header data as well as the payload data. Okay. This is the clock signal. This is the LFD state. LFD state means load first data. What is the first data in a packet? It is going to be the header data. So initially it will be in idle state. If there is no communication, it is going to be in idle state. When it will know that the data is being transferred, it will wait and check for the header data. If it is detecting an address, then it will raise a LFD state. This LFD state will become 1. So it knows that, okay, we have received the data, we have received the address, so there is some data here. So when LFD state is high, you will get the header data through data in. Okay. And after that, it will automatically load the payload data also. So read enable is used when the data is being read from the FIFO. Then this is the global reset signal. And we have one more reset, soft reset. This reset is a global reset. This is a soft reset, which is done internally with the FIFO. When that will happen is, you have the data stored in the FIFO. Actually, FIFO size is 16x9, which means FIFO will have 16 different fields, means from 0 to 15. It can hold 16 values, and each field will have 9. Each field size is 9 bits. So how it will accommodate 9 bits means here you are sharing only 8-bit data, right? What it will do, in order to differentiate between the header and data, it will append one more bit in the LSB. If the detected data is a header byte, it will append 1 to this data and store it in FIFO. If the data it is detecting is a payload, okay, then it will append 0. So that the data, when it is being read from this FIFO, it will be easy to differentiate between the address and the actual data. Okay, so 9-bit data it will store. So what happens is, if the data is available in this router, it will give some valid signals. You will look into another component, synchronizer. In that you can see if there is a valid data present in FIFO, it could be transferred to the destination. So it won't wait for much long time. Okay, it will wait only for few seconds. I think some I'm not sure exactly of how much seconds. It will only wait for few seconds. And if it is timing out, if that valid data present in the FIFO is not read, okay, then it will time out and it will initiate a soft reset to accommodate the upcoming data, because it cannot wait for too long, right? So in that case, it will initiate a soft reset. Write enable means in order to write data into FIFO, we get this write enable signal. So whichever FIFO gets the enable, means write enable, that FIFO will be active at that time. Means that FIFO will be getting the data to be stored over it. So these are the output signals, data out. This is empty. So if the FIFO is empty, if there is not even a single byte stored here, then empty will be 1. If the FIFO is full, full will be 1. If it is half filled, both will be 0. Okay. So next is the FSM. This is the finite state machine. This is going to send the control signals and it will control how the data is going to be added into the FIFO. Okay, so you have many signals here. So first is data in. Here you have only 2 bits. Previously we saw 8-bit data, right? That data is different and this data is different. These 2 bits will denote which FIFO it has to work on. Okay, so 2 bits means obviously it can have 4 different values, 0, 0, 0, 1, 1, 0, and 1, 1. So 0, 0 means first FIFO, 0, 1 will be the second, 1, 0 will be the third FIFO. You can see the block diagram here. This is little clearly visible than the previous one. So 0, 0 in FSM will select this FIFO, 0, 1 will select this, and 1, 0 will select third FIFO. If it is going to be 1, 1 will be invalid. So maybe we can assume that there is no transfer happening. We can keep that for an idle state. Okay. So next we have the clock signal, and MT0, MT1, MT2 are the signals it received from FIFO. In FIFO we saw, right? We have output signal. So this is one FIFO. This will send an empty signal. And similarly, we have 2 other FIFOs as well. So all those empty signals are forwarded here. And also similarly, FIFO full status. Then we have low packet valid signal, parity done. Parity done means, parity checking is completed. And here you can see packet valid and low packet valid. There are 2 signals. Packet valid, you already know. We have already discussed. Low packet valid is exactly opposite to this packet valid. I already said that, see, after the payload are transferred, it will wait for the parity byte. But the packet valid will go low immediately after the last payload. So at that time, low packet valid will turn high, just to denote that the parity matching is going to happen. Okay, so this low packet valid signal is just associated with the parity. Okay, nothing much of that. Then the reset signal and the soft reset signals. And here this is the BC signal. If you can't proceed with the further process, if the router is not ready further, then it will say BC signal detect address. Okay, so once it gets the data here, it will send the detect address for that particular FIFO. So then full state. So that if the FIFO is full, you are getting FIFO full input here, right? Based on that, it will give the full state as an output. Then LAF state. LAF state means load after full. Okay. Load after full state means your FIFO is already full. If your FIFO is full, you can't add further data. So what you will do, you will store the data in a temporary register. So what happens parallelly, the data which is stored in the FIFO will be read, right? It will be read. So slowly the occupied space will become empty. And now the data which is stored in the register can be put inside the FIFO. So in that case, the LAF state will be high, which means it was full previously, but now it is not full. In that case, LAF state can be active. It will be active. Okay. Then LD state is nothing but load data. We previously saw LFD, that is load for, here it is. LFD state means load first data, which means it is only for the header byte. During the first data byte, that is the header byte transfer, this will be high. After the header byte is transferred, this will become low and this will turn high. Okay. So LD state denotes a loading of the actual payload data. Then this is a reset internal register. So based on the software reset, it will initiate the reset if required. Then write enable register means, so in order to enable the write process, write operation, this will give the appropriate signal to that particular FIFO. You got it?
Could you please tell me that low packet valid one more time?
Low packet valid is one, huh?
Yeah.
Okay. So wait, I'll show that. Yeah. Here you have packet valid state, right? you have header, you have payload data. So this packet valid will check only for the header and payload. It won't check the parity bit. So if the header is transferred in the packet, first the header will be transferred. For example, you have 3 payloads. So first header will be transferred, then data 0, data 1, data 2 is transferred. So after that, there is no further data. See, parity is not given by the user. The parity is calculated internally, right? So only the packet value will be high only until the user given data is there. Okay, so it will remain high only till the payload data. It will go low.
Payload.
So in order to capture this transition, whenever packet valid goes low from high to low state, it means parity checking starts, means parity generation and parity checking will start. Okay. In order to denote that, low packet valid signal is introduced and it will turn high. Whenever this packet valid goes low packet valid will turn high.
Okay.
So if low packet valid is high, it means parity operation is going on. Okay. Hope you understood now. Okay.
Okay. Yeah.
Yeah. So this is about FSM. Then we have synchronizer. So it is just synchronizing the data between the FSM, the state machine, and the FIFO. We have so many control signals, right? From the FIFO, we have detect address, and we see all these signals. Based on the signals only, the data is added to FIFO. So it is just providing a synchronization between those control signals and the actual data. You see, it is getting the data in which FIFO it has to select. It will be denoted over this 2-bit data input. Then the clock, then the detect address from the FSM, and the same MT0, MT1, MT2. All these signals it will get from the FIFO only. It will get directly from the FIFO. You can see this in this diagram. You see the MT0, MT1, MT2 from all these FIFO. If you track those paths, and you can see the arrow mark also. Yeah, it goes to the synchronizer, MT0, MT1, MT2. Okay.
Yeah.
Similarly, the full 0, full 1, full 2 status also reaches the synchronizer. So in this way, the data is fed to the synchronizer. It will give those it will give the outputs to the FSM. Similarly, few signals it will get from the FSM and it will redirect it to the FIFO. Means it is acting as an intermediary between the FSM and the FIFO value. Okay. Yeah, so this is read enable signal. If FIFO is available to read enable signal will be given. Write enable register means to write the data into the FIFO. And see here, the write enable register is a single bit data and the output is 3 bits. So how this output will be calculated is by combining the data in and the write enable register. A write enable register, if it is 1 only, then only we can write the data into the FIFO, right? So just assume this write enable register is 1. If the data in is 0, 0, write enable this will be 0, 0, 1. Means it is going to write in the first FIFO. If this is 0, 1, it will be 0, 1, 0. Only the second bit value will be high. Means it is going to second FIFO. If this is 1, 0, third FIFO, then 1, 0, 0 will be the value. So based on the position of 1, we can assume which FIFO it is working with, whether 0, 0, 1 or 0, 1, 0 or 1, 0, 0. Okay, just to select the FIFOs. Then the FIFO full signal, based on this full 0, full 1, full 2, it will generate the FIFO full.
I didn't get that. Could you please tell me one more time?
Which one?
Like
Write enable.
Write enable that 3 bit. How it become 3 bit?
Okay. Here you have write enable register, right? So if the data is going to be written into the FIFO, this has to be high, obviously. But in which FIFO it has to be written? In which FIFO it has to be written will be decided with this data input.
Oh.
Okay. As I already said, 0, 0, 0, 1, 1, 0 are the 3 FIFO selecting values, right? 0, 0 for the first FIFO, 0, 1 for the second FIFO, and 1, 0 for the third FIFO. So if it is 0, 0 in data in and 1 in write enable register, your write enable output will have the value 0, 0, 1.
0, 0, 1.
0, 0, 1, which denotes that the first FIFO is selected. Here, if it is going to be 0, 1, and here the write enable is 1, the output generated will be 0, 1, 0. So it means second one
0,
is
1,
selected.
1 is in 0, 1, 1. 0, 1, 0. Okay.
So not 0, 1, 1. No, it is not incrementing that way. Just the position of the one. See, you have 3 bits. 2. MSB is 2. Then 1, 0. Right. If the LSB is 1, first FIFO. If the first bit is 1, second FIFO. If the MSB, that is this bit number 2 is 1, then third FIFO.
Also 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, like that.
Yeah. That way it will select the FIFO.
Okay.
Okay. So then FIFO full will be calculated based on this full 0 and full 1, full 2. And the soft reset. So yeah, if the data is not, as I already said, if the data is not read from the FIFO, it will time out and it will initiate that soft reset. Then the valid out signal. So valid out signal means if the FIFO has the data, a valid data into it, which has to be read by the destination device, it will say, yes, I have some valid data. Please read me. In that way, the valid out will be sent. Sent based on the value stored in the FIFO. Okay. So this is the synchronizer. And finally, the register. So we know the main purpose of register is to store the values, right? As I already said, if the FIFO is already full, if the FIFO is full and it is not able to take data further, what it will do is, for time being, the data can be stored in the register. See here, you are sending the 8-bit data as input. Means the data is being stored in this register. Okay. So we have clock signal, detect address. So in same way, like how in FIFO it will detect address and store, you have detect address here. It will check if the address is detected, it means, yeah, there is a packet being sent. Then it will also check for FIFO full. If the FIFO is full, it can't take the data further. So the data will be stored in this register. And once the FIFO full value changes, means if there is available space there, then the data will be latched from this register to that FIFO. Okay. Then you have full state, the LAF state, load after full state, the same load data state. All these control signals were sent by the FSM, if you remember, as outputs. So these are given to the register. So it will check based on these states. Actually, it is implemented in the form of state transition only. If I will show you one thing. How to hide this? Okay, I'm not able to show you. Okay, actually there are some states. Okay, state transmission. First, it will check for address. Okay, once address is detected, how the sequence will, in which sequence it will work is, first it will check for the address. If it detects an address, the next state it will go is LFD state. As I already said, it will load the data. Okay.
Will you join for next session, Kirti?
Yes, ma'am, I can join.
Okay, both of you join for the next session.
Okay.